How about just graphing it? Yes. How about just finding the dependence of the length on the thing and it doesn't depend on the mass? Everybody. Differentiated instruction, physics for all. Look at the AP problem. Read and review the problems, because everybody says AP problems, that's real physics. We don't have real physics. So we're going to look at the AP problem, read and review the problem, list the important physics in the problem, and then say what could be understood in that problem from kids prior to the 9th grade, at the 9th grade, at the high school level of the AP, and be prepared to share with the larger group. So this was something which you were going to spend 10 minutes on, but we're going to do it together. There's a problem on an AP exam where it talks about the motion of a person walking from home to school or whatever, and it shows a velocity versus time graph of this. So it's a velocity time graph, goes like this, up, then over, then down, like that. And it asks students to tell the velocity at different parts of the graph. This is AP problem, it's worth 10 points. Tell the velocity at certain parts of the graph. It then asks people to tell me what the distance traveled will be at different parts. Then it asks them to draw a displacement time graph and an acceleration time graph. This is an AP B problem worth 10 points. What could be understood prior to the 9th grade? This is a velocity time graph, and you see this motion. The first question is, what is the speed of the person at t equals 2 seconds? Do you think anybody could answer that before, like prior to 9th grade? It's really, let me see, let's show of hands. How many people think you could? Yeah. I think it's pretty much reading a graph question.
Yeah. But you have to use speed and not velocity.
Yeah, maybe you'd have to use speed. Then the next part of the question is something like, where is the person at rest? Now, I don't think we're at pre-9th grade, because now it's where it crosses the x-axis, right? It's not like this part. It's where it crosses the x-axis at rest. So you have to know it's when the velocity is 0 enough. So I think at the 9th grade level you can do that. It's still qualitative. It's still, do you understand? But you have to understand that at rest means the velocity is 0.
But it's still reading the graph, too.
It's still reading the graph. So it's somewhere here. For kids beyond 9th grade, though, the idea of the display, not the acceleration time graph, which I think we could do at 9th grade, the acceleration time, because it slopes. Here it's a 0 slope. But the displacement time graph, that gets tricky. That I don't think we can expect from 9th graders, because when it's a constant acceleration, you now have to draw it as a parabola. When it's going at constant speed, you now have to have the parabola. And even when you've seen good students do this, they draw a nice parabola, then they have this break. When they know the speed is increased, the speed is constant, so the displacement, but they don't have it continuous. They don't have the slope matching that slope. And then it turns around and stuff, but you have to realize that it's never coming back this way. I think now we're talking about at the high school level, or maybe at the AP level. I'm trying to think of some of the others. Will somebody throw out, and does somebody remember an AP problem? You all know some AP. Yeah, tell me an AP problem.
There's a catapult type problem. This is a seating question, but it's
okay.
Energy, and it's like in this position, a counterweight here with a fulcrum here, and then a cup. You put a ball in the cup, and then you're supposed to calculate the velocity of the ball as it leaves the cup, and then how far it travels.
Great. So I don't know. Let me just repeat it. So you have some kind of lever system here. You're going to put a ball here. This weight is going to go like this. And then the ball's going to release, and then it's going to go in a parabola toward here, and we're going to calculate where it lands, something like that. So now, when we look at the problem, there are certain elements of the problem. One is the conservation of energy when it goes from here to here. Conservation of energy, that a part of that there is conservation of energy, is probably prior to 9th grade or 9th grade, that the potential energy becomes kinetic energy, or this is losing potential energy, that's gaining potential energy. I have to see exactly what it is. But the energy concept, that it is an energy problem and not a force problem at the beginning, is something that 9th graders can do. Can we get 9th graders to look at problems and say, these are force problems, these are energy problems? And I think the answer is yes. If you ever see a roller coaster, where the roller coaster goes like this, don't think forces. They're vectors, they're not going to work. think energy. On the other hand, if you see a question about how much time does it take to go down this incline, don't use energy because it doesn't tell you anything about time. Ninth graders can learn that. Energy is a scalar, force is a vector. So you start differentiating that. And that's the things we can teach. They're big physics concepts. But then at the ninth grade level, it's like, well, mgh equals 1/2 mv squared. Or it has an initial velocity and it falls. How much time does it take to fall? It goes in a parabola. People do that in ninth grade also. When they can calculate, well, you know what? I had a group of ninth graders, my class of personalities. 18 of them were learning disabled. 4 of the others didn't speak English. And I called my class of personalities because there were no 2 kids alike. They were just so different. And we were doing a physics unit and where they had to develop a sport for the moon. And these boys, these special needs boys, had come up with this gladiator sport, which I never quite understood how you played the sport, but I did know the more points, the more blood, the more points. That was kind of the idea. And it's like, well, how do you, so they're engaged. They certainly, they're like, I can't believe he's letting us do this. Like, but then when they explain to the class what they did, they see, and then you rip the guy's arm off on the moon, and the blood is coming. You save the blood because that's the points. Then you hurl the arm across the stadium, and we can now explain to you that it travels in a parabola and where it will land. So they were able to do that. Ninth grade special needs kids were able to tell me the trajectory and do that. It took them a while. They're not. So they can do that. But then, though, that problem becomes rather sophisticated with this and that. But there are parts they can do. And if you're doing it in ninth grade and you're telling the kids, let me show you an AP question, which again everybody thinks is real physics. Here's an AP question with 10 points. You can get 3 points here in ninth grade. When you take AP physics, you can get all 10. Not if you take AP, when you take it. It's not so hard looking at 3 points right now. Demystify the AP. So let's look at math or physics. This is where the problem comes up with, is it real physics? Vectors. We need to be able to add vectors and to take vector components. It's important to understand that a force is a vector and it can be broken up into components, or to be able to add forces. Oh, also in that ninth grade thing, you can probably draw a force diagram, and ninth graders can do that. Where are the forces? Free body diagram. I would tell you that you can do all the physics necessary if you limit yourself to 30, 60, 90 triangles with corresponding sides of 1, 2, and 0.85, and 3, 4, 5 triangles with corresponding angles 37, 53, and 90 degrees. That's a lot of stuff. That's a lot of choices. You can have the 30, 60, 90 triangle this way, or you can have it that way. They'll know how to do the vertical and horizontal component, but they'll know it's always 3, 4, 5, or 30, 60, 90. And yet there are physics people saying, no. They have to be able to take the sine of 25 or the tangent of 17. That's real physics. And I'm telling you that has nothing to do with physics, it has to do with math. There is nothing they're learning about physics, but by making them do it with 17 degrees, you say, oh, you don't know 17 degrees? You can't do physics. It's not true. It's not physics, it's math. And we have to distinguish between those two things. Now, first of all, I love physics. Eugene Wigner, Nobel Prize for Group Theory, said, the unreasonable effectiveness of mathematics in explaining the physical world. Why is it that math explains the physical world so well? It didn't have to. It just does. Galileo found it did, and everybody since then has just been amazed that it does. That resonates with me. I love math and I love physics. Not everybody else does. And physics should not be the second math course of the day. Because too many of the kids think, oh yeah, I'm going to my second math course of the day, physics. There's a lot of physics that's not about more mathematical sophistication. Now, here's what happens as physics people. Because most of us were also good at math, we think it's really easy to do. So what happens is, we think, you know what, I can teach them. In a little bit of time, I can teach them. Because it's not that hard. We're wrong. You can teach in a little time. And I want you to think about this, like this idea of like F equals ma, that's the same as A equals F over m. Oh, they should be able to do that. I can teach them that. There's a math teacher down the hall who's been working 2 months to get them to do that and not having too much success. Why do you think you'll be able to do it in a day? So, I don't want to go on because I really want you to learn this math. Please, I'm sure you can get it in one more day. No, they're not going to get it. I have kids who couldn't do some of the math, and what I say to them is, listen, I hate to pick on you, I don't even know you. You're having trouble with the math. Tomorrow's test, when you see that question with the math, don't even do it. Just skip it. Because you're going to spend 20 minutes of that, and you're still going to get it wrong. Go for a 90 on the test. Leave that question out. I think you can get a 90 without that question. It's like, okay, that's what you do. Don't say, oh, you better. No. 2 months they're trying to do this. What are our alternatives? Well, there are alternatives in instruction. Most of us, d equals 1/2 at squared, t equals square root of 2, we say, that's the same equation. For most kids in America, these two equations have no relation to each other at all. No relation at all. And in fact, if you insist on this second equation, because, well, they have to be able to solve for the time, if you insist on the second equation, they have lost, you have robbed them of some of the beauty in physics. There is only one equation, this one. It tells you how far something falls in a given amount of time. There is one equation. That's the beauty of physics. One equation describes freely falling objects. One. Not two. One. And no matter how much you tell them, well, they're the same, they see it as two. Physics is no longer as elegant. But what do? Well, here's what we do with the learning disabled special needs ninth graders. We used to do a lot of problems. Let's drop a ball from 2 seconds and calculate the distance. A is 9.8, we'll make it 10, so a half, so it's 5t squared. And we did lots of problems with that. Anytime I threw out a number, 3 seconds in their calculator, 2.7 seconds in their calculator, they could tell me the distance anything would fall in. And you made up a time, whatever, they could tell you the distance it would fall. Didn't even take them that long. They got really good at it. Then I said one day, after they were good at it, I said, oh, how long does it take something to fall from 50 meters? And they said, no, we don't do that. And I said, what do you mean? They said, no, you give us the time, we give you the height. And I said, well, no, but somebody asked me about 50 meters, and I said, you'd be able to do it. And they said, how? I said, you know what, let me think. I think it's 2 seconds. And they said, no. I said, why not? They said, no, 2 seconds is 20 meters. I said, oh, we want 50 meters. Try 3 seconds. 45 meters. Try 4 seconds. 80 meters. 50 meters. So what's it going to be between 3 and 4? Try some numbers and tell me what it is. And they were really quick. And it was like 3.2. It's like, can you give 2 to the hundredth? 3.23. They can solve the problem numerically using one equation. Just keep trying times until you get the 50 meters. And you know what? They'll do it faster and more accurately than most of you students who are struggling with this equation and also need the calculator for the square root. And they can do it to any accuracy you want. And there's one equation, and they can do it. We need more of these tools to teach physics and not make it math. My Michael Faraday story. Michael Faraday is, we all know Michael Faraday. So in the 1800s, Oersted in 1810 had found out that electric currents produce magnetic fields. And then everybody was out for the big thing, can magnetism cause electricity? This is a big question. And there was Michael Faraday, a bookbinder, dropped out of school at 14, to bind books, because that was a job and he needed a trade and he didn't have any money and stuff like that. So Michael Faraday was binding books, and one of the books they were going to bind to sell was a book on all these papers on electricity and magnetism, so people could then, this would be like a big seller among physics people.